we will discuss Burgess circuit. We have already discussed Burgess vector, and the Burgess vector we define currently as magnitude and direction, a vector representing magnitude and direction of the slip. Magnitude and direction of slip. We have defined dislocation as the boundary between slip and no slip region on a slip plane, and the slip is characterized by this Burgess vector giving its magnitude and direction. But there is another way of looking at Burgess vector independent of the slip, and that was originally given by Burgess, a person who is quite famous in fluid mechanics. He has contributed and he has lab named after him in his country Netherlands, but he also contributed one paper in this dislocation, and that is on Burgess circuit. So, let us look at Burgess circuit, what is meant by Burgess circuit. So, imagine we are looking at the front face of a simple cubic crystal with atoms arranged in this square grid. Of course, you will have a 3-dimensional crystal. So, atoms will be into the crystal also, but I have not drawn. So, we are seeing the front face, and let us on this front face draw a circuit. Let us draw a circuit. Let us try to draw a closed circuit. Any closed circuit will do. So, for sake of simplicity, I am keeping it rectangular circuit. Let me keep track of the direction. So, I am going clockwise, and let me say this was the start and this was also the finish point of my Burgess circuit, and let me count the steps. So, I have steps 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So, I have gone 16 steps to the right, and then how many steps down? So, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, 16 steps to the right, 10 steps down, then I have again taken 16 steps to the left and 10 steps up. So, this is a complete rectangle, and in a nice crystal like this, I have a closed Burgess circuit. Now, I do this exercise again rather boringly. I try this again on this crystal. So, I again have a start point. I had gone 16 to the right. So, I take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So, I go up to the 16. Let me be sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 and 16. 16 steps to the right, and remember we had gone 10 steps down. So, I come down 2, 3, 4, 5, 6, 7, 8, 9, 10. I reach here. Then I again go 16 steps to the left, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 and 10 steps up. I have not completed the circuit. Am I doing something wrong? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, it is 16 by 10 rectangle in this crystal also, but it is not completing, it is not closing. So, there is a closure failure. What is the reason for this closure failure? So, the reason for the closure failure is hidden behind this sticker. So, let me remove this sticker, and what you find is that this crystal is having an extra half plane. That was the reason for the closure failure. This is an extra half plane. So, the number of planes above was more than the number of planes below. So, this is the property of a Burgess circuit. A Burgess circuit, in the original picture, nothing was hidden behind this thing, there were planes were continuous. So, I had a perfect crystal and I had a closed Burgess circuit on the perfect crystal. But if such a circuit is mapped, so a closed circuit a closed Burgess circuit in a perfect crystal fails to close when mapped around a dislocation line. So, this is what you are seeing, and that closure failure, let me draw this closure failure as a vector. So, if I go from finish to start, I go to this vector, which is exactly one interplanar spacing. And remember, in the slip picture also, with this edge dislocation, we had introduced a Burgess vector, which was one interplanar spacing. So, the closure failure is nothing but the same Burgess vector which I had obtained by the slip approach. So, the closure failure is equal to the Burgess vector. So, a closed Burgess circuit in a perfect crystal fails to close when mapped around a dislocation line, and the closure failure in this case finish to start is the Burgess vector. One thing to keep in mind about the Burgess vector is that the magnitude of the Burgess vector and the line along which it will appear is fixed. So, for example, in this picture the Burgess vector will always be along horizontal line. I will never get a Burgess vector which is this for this dislocation line. Burgess vector will always be horizontal, and its magnitude will also be always this one interplanar spacing for this dislocation line. However, the sense can reverse. Suppose I had taken my circuit not clockwise, but anti-clockwise. If I had started and gone all the way round in a different direction, instead of clockwise, anti-clockwise, then I would have got a Burgess vector which would have been pointing in the opposite sense. So, the Burgess vector depends upon the way I define my circuit, whether I am taking my clockwise circuit or taking anti-clockwise circuit, or even taking this clockwise circuit, I could have defined, there was no reason to define the Burgess vector as finish to start. I could have defined the Burgess vector as start to finish. In fact, some books will define that way. So, start to finish. So, that also is a proper Burgess vector, and this is because in the slip approach also the magnitude and direction of the slip is not uniquely defined. Whenever there is a slip, there is a relative slip. So, an upper part of the crystal is slipping with respect to the lower part across a slip plane. So, if we look at the motion of the upper part, that will be in one direction. If we look at the motion of the lower part, that will be in the opposite direction. So, Burgess vector has a fixed magnitude and direction, but the sense can be either one way or other way. This ambiguity is always there, and to avoid this ambiguity in any one given discussion or in one literature, one defines what is called the Burgess vector convention. In our course, we will take a Burgess vector convention that our closed circuit is in a perfect crystal, and we will take the circuit clockwise right hand circuit with thumb pointing in the direction of T, the tangent vector. See, the tangent vector also has an ambiguity. If I have a dislocation line, I said a unit vector parallel to the dislocation line is the tangent vector, but then tangent vector can be selected this, or somebody could have selected the tangent vector like this. So, the tangent vector also has an ambiguity. So, first you have to select a tangent vector, and once you have selected a tangent vector, with respect to that tangent vector, your circuit can be either right handed or left handed. In this convention, in our convention, we are taking a right handed circuit. So, if you curl your fingers again of your right hand such that the thumb points in the direction of T, then the fingers will be circling in the direction in which you should take the circuit. So, right handed circuit with thumb pointing in the direction of T, and then the closure failure finish to start will be the Burgess vector. This is sometimes shortened into name RHFS convention. So, we will be following this convention in all future discussion, but when you are looking up other textbooks or other literature, you should make sure what is the convention of the Burgess vector they are using.